Welcome to the solutions to the Regents Physics Current Electricity problem set, problems numbers 1 through 7. Let's go ahead and jump in here. We have some introductory questions here on current electricity. Number 1, when a battery is connected to complete a circuit, charges flow in the circuit almost instantaneously. Explain why. Your explanation should include that the battery does work to move electrons from the positive terminal to the negative terminal. This work causes the electrons to take the place of electrons ahead of them and therefore cause a current to flow. If you need help with this explanation, ask and we'll expand on this in class tomorrow. Number 2, why can birds perch on high voltage lines without being injured? We see this happen all the time, where you might drive past and see a hawk or some Tweety bird or whatever on a high voltage power line. And how is it that they can be attached to that high voltage power line and not be electrocuted? Well, the trick here is that there is no difference of potential across the wires between their legs, and therefore no charges flow. So if we take a look here, for example, let's hypothetically say that there was a voltage of 10,000 volts in the line. Well, the potential at one bird leg would be 10,000 volts, and the potential at the other bird leg would be also 10,000 volts. So what there isn't is a difference of potential, and that's what you need to have in order for a current to flow, is a potential difference. Now, if one of these birds were to hop over and, for example, see a bug on this piece of wood over here and peck it with his beak, then he would be touching something with zero potential while sitting on something with 10,000 volts of potential. Then there would be a potential difference, and that bird would be electrocuted in probably a puff of feathers. So if you don't understand this, again, make sure you ask in class tomorrow. Number 3, describe 2 ways to increase the current in a circuit. What this is asking you to do is to apply Ohm's law here. And Ohm's law is R equals V over I. Well, solving that for current using any of the ways in which you've been taught, you can use the Indian sees the vulture over the rabbit. You can use the circle chart that was taught to you in your lesson. Okay, or you can just solve for I algebraically. From Ohm's law, R equals V over I would be equal to V over R. So if you want to increase the current, the 2 ways to do that is to see that current is directly proportional to voltage. So one way to do it would be to increase the voltage. Current is indirectly or inversely proportional to resistance. So if you wanted to increase the current, you have to decrease the resistance. Number 4, if the voltage across the circuit is kept constant and the resistance is doubled, what effect does this have on the circuit's current? So once again, we take Ohm's law and solve it for I, and I would be V over R, and this says that the circuit's voltage is kept constant, so it's equal, but the resistance is doubled. Okay, so by doubling resistance with an inverse relationship between R and I, if R increases by a factor of 2, that means I would decrease by a factor of 2, or be halved would be another way to say that. Number 5, what is the effect on the current if both the resistance and voltage are doubled? We go ahead again. We use Ohm's law, solved for current, I equals V over R. And this says that both the voltage is doubled and the resistance is doubled. So by doubling both, you can see that the 2's would cancel and the current would not change in this particular case. So a good series of questions there, testing you on changing variables in Ohm's law and what is the impact on the current. Now let's get into some problem solving. Sue finds a device that looks like a resistor. When she connects it to a 1.5 volt battery, only 45 times 10 to the negative 6 amperes is measured. But when 3 volts is used, 25 times 10 to the negative 3 amperes is measured. Does the resistor obey Ohm's law? Well, up in here you've got voltage, and amperes is the measure of current, voltage and current. So the way to solve this question is to use Ohm's law, R equals V over I, and solve for the resistance of the resistor in each of the cases described. So at 1.5 volts, when we connect it to the 1.5 volt battery, R would be 1.5 divided by 45 times 10 to the negative 6. This would give a resistance of 3.3 times 10 to the 4th ohms. At 3 volts, the resistance would be 3 volts divided by 25 times 10 to the negative 3 amperes, and this would give 120 ohms. In order for the resistor to obey Ohm's law, that is to say that it's ohmic, another way to say that, means that the resistance would have to remain constant as voltage and current increase. Okay, that the relationship between V and I would be linear and therefore directly proportional. This is showing that this particular resistor, the resistance does not remain constant, so no, the resistor does not obey Ohm's law. In number 7, a current through a toaster connected to a 120 volt source is 8 amperes. What power is dissipated by the toaster? Okay, so it's a great practical question here. We have a 120 volt source, which is the same as the wall electricity in your house. And we have a current of 8 amperes, which is pretty much standard for toasters such as the one pictured. They want to know what power is dissipated by the toaster, or in other words, what power is used up by the toaster, or what power is required to operate the toaster. Both mean the same thing, okay, or are equal to each other. Well, looking at your reference table for power, power is capital P. You're provided V and the current, which is I. So you would use P equals V times I right off the reference table. The voltage is 120 volts. The current is 8 amperes, and 120 times 8 is 960. Notice the unit of power here is watts, capital W for watts, just like you learned earlier this year when we were doing mechanics. All right, that'll do it on our solutions for problems 1 through 7. More to come on a couple introductory questions when we do problems 8 and 9 together in class tomorrow.